Hello, friends, and welcome. If you're preparing for the CSIR Net Earth Sciences exam, you know just how vast the oceanography syllabus is. That's why we've analyzed the last 5 years of exam papers to pinpoint the topics that come up again and again. So let's dive in and decode these high-frequency topics. So what are these favorite topics of the CSIR paper setters? Well, our detailed analysis shows some really clear patterns. And listen, this isn't guesswork. It's a data-driven strategy designed to give your preparation a serious boost. All right, here's our game plan. We're going to start with the game of currents. Then we'll get into the language of waves. After that, we'll cover the ocean's chemical fundamentals and productivity in food chains. And finally, we'll look at how past clues can give us future hints. Okay, let's kick things off with Section 1, the game of currents. We're talking about the massive rivers flowing within the ocean and what drives them. This is a core topic, so you'll want to pay close attention here. Now, this is an absolute favorite for comparison questions in the exam. On one side, you have western boundary currents like the Gulf Stream. They're warm, fast, narrow, and deep. On the other side, eastern boundary currents like the California current. They're the complete opposite. Cold, slow, wide, and shallow. You've got to remember this contrast. Next up, Ekman transport. The most important thing to remember here is this. The net movement of water is at a 90-degree angle to the wind direction. It's to the right in the northern hemisphere and to the left in the southern hemisphere. And this is the main engine behind coastal upwelling, which, supports our fisheries. Just look at this number, around 130 sverdrups. That's the sheer power of the Antarctic circumpolar current. So what's a sverdrup? It's 1 million cubic meters of water per second. So we're talking about 130 million cubic meters per second. It's the largest current on Earth, so yeah, you can bet questions are going to pop up about it. All right, let's move on to our next section, the language of waves. And no, we're not talking about the waves you see at the beach. We're talking about those massive planetary waves that examiners love to ask about, specifically Kelvin and Rossby waves. The key difference here is really clear. Kelvin waves travel eastward, right along the equator or coastlines, but Rossby waves, these are the planetary giants, they always travel westward. Here's a super simple trick to remember it. Rossby runs west. The questions are almost always about the direction, so just lock that in. Another really important comparison is between deep and shallow water waves. In deep water, the particle motion is circular, and the wave speed depends on its wavelength. But in shallow water, the wave actually feels the bottom. So the particle motion becomes elliptical, and the speed depends only on the water depth. Simple as that. And that brings us to Section 3, the ocean's chemical fundamentals. We're shifting gears now from physics to chemistry, and two topics really dominate here, the Redfield ratio and ocean acidification. You absolutely have to know the Redfield ratio. It's basically the fundamental recipe for life in the ocean. For every 106 carbon atoms, phytoplankton needs 16 nitrogen atoms and 1 phosphorus atom. This 106-16-1 ratio of C to N to P is what links biology, chemistry, and nutrient cycles all together. Understanding the process of ocean acidification step by step is crucial. First, atmospheric CO2 rises. The ocean absorbs about a quarter of it, which then forms carbonic acid. This lowers the ocean's pH. But here's the most critical point. Step 4. This process uses up carbonate ions, which organisms like corals need to build their shells. Less carbonate means weaker shells. And what about the oxygen minimum zone, or OMZ? Why does it form? Well, it's created by a kind of perfect storm of 3 factors. You've got high productivity at the surface, meaning lots of life. When these organisms die and sink, bacteria decompose them, using up oxygen. Add to that the fact that water mixing is really slow in that zone. These 3 things together create a zone where there's almost no oxygen. And that's a perfect lead-in to Section 4, productivity and food chains. We've talked physics and chemistry, so now let's see how biology, life itself, works in the ocean. A classic exam topic is the North Atlantic spring bloom. In the winter, deep mixing brings nutrients up to the surface, but there isn't much light. Then comes spring. The water column settles into layers, trapping those nutrients in the sunlit zone. The result? A massive explosion of phytoplankton. And right on their heels, the zooplankton population peaks to graze on them. It's this beautiful, predictable cycle. So are all ocean food chains the same length? Absolutely not. In nutrient-rich upwelling zones, you have large phytoplankton. This leads to a short, efficient food chain. These phytoplankton are eaten directly by fish like anchovies. But in the deserts of the ocean, the oligotrophic gyres, it all starts with tiny picoplankton, which means it takes many more steps to get to a large predator.
And now for our final section, past clues, future hints. In paleoceanography, we use geological records to understand how the ocean and climate system worked in the past. This gives us essential clues for the future.
Tectonics can completely change ocean circulation. The biggest example of this is the opening of the Drake Passage, about 34 million years ago. This separated Antarctica from South America and created the Antarctic Circumpolar Current, the one we talked about earlier. This current thermally isolated Antarctica, which led to the formation of massive ice sheets and kicked off global cooling. So how do we know all this? We use proxies, like oxygen isotopes or delta 18O. Now, the most interesting thing about this proxy is its double meaning. When we find more heavy oxygen or a higher delta 18O in old shells, it can mean one of two things. Either the water was colder or there was more ice on the planet. That's because the lighter oxygen isotope gets trapped in ice sheets. Understanding this dual meaning is absolutely critical for proxy-based questions. Okay, let's do a quick rapid-fire revision. Western currents, warm and fast. Eastern currents, cold and slow. Ekman transport, 90 degrees right in the northern hemisphere, 90 degrees left in the southern. Rossby waves, run west. The Redfield ratio, C to N to P, is 106 to 16 to 1. A higher delta 18O means a colder climate or more ice, and the opening of the Drake Passage led to global cooling. Got it? Awesome. So we'll leave you with this question. We've talked about currents, chemistry, life, and the deep past. But out of all these interconnected topics, which one do you think holds the biggest key to understanding Earth's future climate? It's a big question, and it really highlights the relevance of this field today. Thanks for tuning in.